Hello everyone, I am Aloysio Dourado and I will present our domain adaptation for holistic skin detection paper. Human skin detection is the task of identifying which pixels of an image respond to the skin. There are several applications for segmentation of skin regions in images, like video surveillance, people tracking, human-computer interaction, face detection, and recognition and gesture detection, among many others. Despite all advances that fully convolutional neural networks have brought for image segmentation, some common criticism is still made to argue that pixel-based approaches are more suitable for skin detection, namely, the need for large training datasets, the specificity or lack of generalization of neural nets, and prediction time. In this paper, we addressed all those criticisms with a series of comprehensive in-domain and cross-domain experiments. Our experiments show the effectiveness of the proposed strategy and confirm the superiority of FCN approaches over local approaches for skin segmentation. The main contributions of our paper are the proposal of a new domain adaptation strategy that combines pseudo-labeling and transfer learning for cross-domain training, a comparison of holistic versus local approaches on in-domain and cross-domain experiments applied to skin segmentation with an extensive set of experiments, a comparison of CNN-based approaches with state-of-the-art pixel-based ones, and experimental assessment of the generalization power of different human skin datasets. Skin segmentation approaches may be classified into two main groups, local and holistic approaches. Local approaches considers only a small area surrounding the point of interest to classify all the pixels in the image, one by one. In a pixel-based approach, the region that is used to classify each point of the image is a single pixel. Different approaches use different color spaces as input to the classification model. The classification model is usually executed several times to classify all the pixels in the original image. In patch-based approaches, a patch surrounding the pixel of interest is used to classify each point of the image. To classify all the pixels of the input image, a sliding window is used to extract the patches for each pixel. The classification model is then executed several times to classify all the pixels. The main advantage of patch-based over pixel-based approaches is the addition of texture as information for the classification. For the patch-based approach, the model is usually a classification convolutional network that classifies the center pixel of the patch as skin or not skin. In holistic approaches, all the image is submitted to an image segmentation model, usually a fully convolutional network, and all the pixels are classified in a single shot by the model. In addition to color and texture, holistic approaches adds contextual information that is expected to improve skin detection. In this paper, we compared a local CNN patch-based to a holistic FCM approach. Training data is usually a main concern when using deep learning approaches. There are some existing skin detection datasets. However, each one of them presents a different level of quality, illumination, and other characteristics. Besides that, each dataset presents different kinds of images, general web images, portraits, surveillance cameras, etc. The differences are so relevant that each dataset may be considered as a different domain. Training on a domain and evaluation on another dataset usually leads to poor results due to marginal probability differences of the two domains. However, one may apply domain adaptation methods to reduce undesired effects. In this paper, we evaluate the use of domain adaptation to overcome the data availability problem, using an existing large and diverse dataset to train a network to a domain with few training data. We use a 3-convolutional layer network with max pooling between convolutions and rectified linear unit activation function between inner layers to reduce the vanishing gradient effect. The output of the network consists of 2 fully connected layers and a sigmod final activation for binary classification. Due to its simplicity and performance, we used UNet as the holistic segmentation method. Our model follows the general original design, but we use a 7-level structure with addition of batch normalization between the convolutional layers. To exploit domain adaptation techniques for the problem of training data availability for skin segmentation, we evaluate 3 domain adaptation techniques. The fine-tune approach consists of using the learned parameters from the source domain as a starting point for the optimization of the parameters of the network on the target domain. The optimization first focuses on the modified output layer, which is intimately linked to the classification task. Other layers are initially frozen, working as a feature extraction method. Next, all parameters are unfrozen and optimization carries on until convergence. In this work, we propose a method that relates to pseudo-label approach, but instead of using the same model and domain for final prediction and pseudo-label generation, we use a model trained on a different domain to generate pseudo-labels for the target domain. These pseudo-labels are then used to fine-tune the original model or to train another model from scratch in a semi-supervised manner. We call this technique cross-domain pseudo-labeling. Our last approach consists in combining fine-tune and pseudo-labeling approaches in order to improve the final model performance. We use weights obtained from a cross-domain pseudo-label model to fine-tune a model that is used to generate a more accurate set of pseudo-labels. These new pseudo-labels are then used in one domain pseudo-label training round to get the final model. Here, we compare our CNN-based local and holistic models in same domain training situations to previous color-based local models and FCN-based holistic solutions. In same domain setups, the models are trained and evaluated on the same dataset. The in-domain results clearly show the superiority of data-centric deep learning solutions over traditional color-based approaches. Regarding holistic approaches, our FCN achieved the best F1 score on SFA and VPU. In all datasets, the best model was a holistic approach. To evaluate the effect of using domain adaptation techniques over deep learning models in low training data situation, we used our UNet holistic model in several cross-domain setups, using different levels of labels from target domain. Target-only results are provided as baseline scores. As cross-domain sources, we used compact and Pratipan datasets as they are most diverse and presented more generalization power. Given the superiority of FCN-based holistic approaches, for now on, we focus on our UNet model. We evaluated the effect of changing the amount of training data and present results ranging from 0 labels to all labels. COMPAC has confirmed our expectations of being the most generalizable source dataset, not only for being the most numerous in terms of sample images, but also due to their diversity in appearance. The use of COMPAC as source leads to very good results on SFA and Pratipan as target. Note that when using COMPAC as source and Pratipan as target, the gain of the domain adaptation approach is very expressive when compared to target-only training. Domain adaptation methods got better results using any amount of labels on the training set, being the combined approach the best option in most cases. Using 50% of training data, our cross-domain pseudo-label approach was better than regular supervised training with 100% of training data. On the other hand, VPU confirmed our expectation of being the most challenging dataset for domain adaptation with pseudo-labels due to the domain shift level. However, substantial gains were observed with regular fine-tuning. Qualitative results. Using domain adaptation from COMPAC to SFA leads to impressive results, even though using no labels from target. This observation completely refutes the criticisms of needing large datasets for training and lack of generalization power of deep neural networks. Another important aspect to be addressed is the criticism for the applicability of CNN approach for real-time applications. This is probably valid for PET-based CNN approaches, but it does not hold for our FCN holistic approach. The average prediction time of our PET-based CNN using a simple NVIDIA GPU with a frame size of 768 by 768 pixels is 7 seconds per image, which is indeed not suitable for real-time applications. However, our UNet prediction time is 8 milliseconds per frame for the same setup. In other words, 12.5 images are processed per second without using parallel processing. Conclusions. In this work, we refuted some common criticisms regarding the use of deep convolutional networks for skin segmentation. The criticisms regarding training size and generalization power were refuted by using domain adaptation techniques to explore labeled data from other domains. The criticism regarding execution time was refuted by using an efficient, holistic FCN. Besides that, we proposed novel approaches for semi-supervised and unsupervised domain application applied to skin segmentation using CNN and evaluated it with an extensive set of experiments. Our evaluation in domain skin detection approaches on different domains confirmed the expected superiority of CNN or FCN-based approaches over color-based. Thank you.